Okay, ultimately mistake failure. This is kind of yeah. This is one that I kind of like. I think it's kind of cool. So I'm opening this model again, okay? And I'm gonna add a sensor here, and this is gonna give me the maximum normal stress in the tubular tower. And we can also look at the stress distribution. So I start my simulation now, and we can see. So you can see, so the color here is telling you how much stress the elements have. Okay, so you can see that the turbine is kind of oscillating, and when it's oscillating, then you get a little bit of blue here, but mostly we have like quite low stresses here. This is a dynamic simulation, by the way, so that's why you get this oscillation, right? Because we're modeling something that's happening in time simulation. We could do a static analysis, but because of what I want to show, I chose the time simulation. And this oscillation is just the wind turbine kind of moving back and forth, right? This actually, I'm pretty sure that if I check, this is going to be the first natural period. And you can see that, here, this is about, 2.9 seconds, and the next peak is about 6. So if I go and check the eigenfrequencies of my wind turbine, which you can do here, we're going to see that, yeah, so this is the mode that we're looking at. And indeed, the eigenperiod is 3.1 seconds. Cool. So I start my simulation again. I have my maximum stress here. What is going to happen if I increase the wind speeds to this graph? In terms of the kind of the steady state value, not like the oscillations, but you have 3 options. Either it's going to increase, it's going to stay the same, or it's going to decrease, or something else. I don't know what that would be, but any guesses? The trick question. Increase. Okay, let's see. We have a couple of increases. So now increase the wind speed. It's a pity that the simulation is running so slow. But anyway, so as you saw, yeah, so you increase the wind speed, and then you get like a couple of oscillations, but then it's gonna decay to a nice steady value, which is higher than what it was. Cool. So yeah, very nice. You dodged the first question. So the next question is, what happens if I increase the wind speed? Which sounds pretty much like the previous question. I mean, it is the same question, but it's gonna be different results. So I'm just gonna show it to you. If I increase the wind speed now, so again, you get like these transients, which you get some transients, but actually the value at which we're gonna end up is lower than the previous one. And this is quite counterintuitive, and it's quite interesting that, I mean, lots of people get it wrong. Like even people that kind of work with wind energy, it's something that's counterintuitive, and it will keep happening. So if I keep increasing the wind speeds, it's just gonna kind of keep decreasing and decreasing. And yeah, I changed the wind speed. Yeah. It went down. 11, 12. It went down. It up and then down. Look, I'm going to show you the wind speed, okay? Let's see. I have the wind speed here. So this is the wind speed. So the wind speed was at 10. Increase the wind speed, increase the maximum shear. Increase the wind speed, decrease the maximum shear. Increase again, decrease again. Okay. And I could keep doing this. I could keep like increasing the wind speed, and then the shear is gonna decrease. So do you have any idea of what happens, or should I just yes. Sorry? It has to do with the it's not a coupling effect, but it has to do with the blades having changed. Yeah, correct. It's a pitch angle. So someone said it's the pitch angle. Yes, it's a pitch angle. Spot on. So I'm going to show you a couple more graphs. One is the power that we're producing, and the other one is the pitch angle, which is here. So let's have a look at the graph first, at the power first, okay? So you can see that we were at 10 meters per second, and then my wind turbine was producing 3.5 megawatts. We increased to 11 meters per second, and then we were producing 4 and something, 4.5. And then when we increased, we reached 5 megawatts. And then it stays constant at 5 megawatts from then on. This wind turbine has been designed to produce 5 megawatts. So you don't, even if the wind is stronger, you're not going to produce more. And that's because, well, for several reasons, but mainly financially, it made sense to design a generator and cables and a whole system that can cope with 5 megawatts, but not more than that. And yeah, if the wind is stronger, you're actually wasting energy, but that doesn't happen often enough that it makes it worth designing a bigger wind turbine. Does that make sense? So the way you try to keep the power constant is by pitching the blades. So you can see now, I mean, the pitch is quite small. It's about 10 degrees, so I don't know how much you will see it, but yeah, you can see that the blades are a little bit pitched, and this is kind of the way it works. This is the way all modern wind turbines work, is that you actually decrease the efficiency. So if I show you the efficiency, which is this power coefficient here, yeah, maybe I can delete a couple of graphs. This is the efficiency. So we started at 50% efficiency, which is quite good for for a wind turbine like this. And then that's kind of the maximum that you can do. And once you reach your maximum power, you're purposefully decreasing your efficiency. So you're not taking as much, wind energy as you could. So yeah, so that was the explanation for this one. Does this, yes?
So the question is, there is a mechanical system inside the blade that when the power goes to 5 megawatts, so slowly it rotates the blade. So it's a mechanical movement.
Correct. Okay. Yeah. So yeah, there is the question was whether there is a mechanical motor inside the blades that actually turns pitches the blades. And yes, that's the answer is yes. That's how it works. Do you see these little peaks here? So there's like lots of little peaks here. So these, well, do you want to guess what it is first, and then I can say it? Yeah. Yeah. Spot on. Yeah, it's the blade passing the tower. So every time the blade passes the tower, you can see that the aerodynamic loads, which are these blue vectors, so this is the thrust, you can see that they decrease a bit. And that's because the tower is kind of blocking the wind, right? So the wind has to go around the tower, and that's slowing down the wind just in front of the tower. That's called the tower shadow effect. And it's very important when you're designing your controller. So when you're designing the system that is going to decide how fast the rotor is rotating and how to pitch the blades. When you design this, it's very important that you make sure that the frequency of this tower shadow, the blade passing frequency is called, doesn't match the eigenfrequency of your support structure, because otherwise you could get resonant effects. Okay. Yeah, I'm going to move on to the next one, unless anyone wants to ask something. Cool. So let's move this, and yeah. Okay. So actually, so when I was talking about doing this seminar, like someone told me, oh yeah, there's this picture of a wind turbine that broke probably because of a storm or something, and it was this picture, and that's that is the misconception. So the maximum loads on the tower, like the maximum stresses, don't occur in the storm. They occur when you're the closest to the rated wind speeds, to your rated conditions. In this case, it's 11.4 meters per second. When there's a massive storm, the blades start pitching, and then the loads on the tower are actually really low. So yeah, so this is what I put these pictures, because it's common to get it wrong. And actually, if you zoom in here, what you see is that what broke is it's actually the foundation itself. So I think that you guys know much more than me about this. But yeah, what broke here is like the way it was anchored to the ground. Cool. So okay, yeah, again, some information on a YouTube video. I mean, I'll share the slides later anyway. Yeah, I don't have that much time left. I'm gonna talk quickly about fatigue. So when you're running, so what we saw right now was ultimate limit state. What's the Oh, well, actually, I could show you. I should show ultimate limit state on an offshore wind turbine, because it's the results are quite different. So if again we show the stresses here, so the maximum stress, I can plot them both in the same graph and show this again. So right now we're at 10 meters per second. Can set it to 11 meters per second. So now we're quite close to this rated wind speed. So we're quite close to producing 5 megawatts. So as we saw before, this is the situation in which we get the maximum stress in the tubular tower here. Okay, and in this particular context, for this particular model, it turns out that the stresses in the tower, which is red, or the maximum stress in the tower, is larger than the maximum stress in the monopile, which is this one. The monopile is this part here, okay? Is the part of the support structure that goes underwater. So you have this part underwater, the monopile, and then you put a tubular tower on top, which is the higher part. This is what happens in operating conditions. This is like a normal windy day. This is what we get. If you have a massive storm, the simulation doesn't look like this at all. What would happen is that you would have the turbine, what we call idling. So the blades will be pitched 90 degrees. Oops, sorry. Did I not press? Yeah, I think I didn't press enter. So the blades would be pitched 90 degrees because, as we explained before, you're trying to avoid getting too much too much wind loads in your wind turbine. And yeah, I'm just gonna remove the control system so that this stays as it is. And you would also get some massive waves, not like what we have here. So for that, I could say that I want these nonlinear waves that are called stream function waves. So if you know what this means, that's really cool. If you don't, it's just a massive wave. It's just a big problematic wave. Okay, so now I have this stream function wave, and now you can see. So I mean, now we have very little loads from the wind. Well, I guess also because the wind is relatively small. In a storm, the wind might be bigger, but we have relatively small loads from the wind. So we have very small stresses both in the tower and in the monopile. But now when these big waves come in, then you're going to see that the stress really increases. And now, so what changes now is that the maximum stress is not in the tubular tower anymore, is in the monopile. So now you're in a situation where the hydrodynamic loads, so the wave loads, are actually what are being problematic, and is what is driving the design. You also see some some kind of decay effect where you have a big load, you start moving the turbine, and then it kind of oscillates a bit, which is something that you have to look into. But yeah, so that's what I wanted to say, is that if you move offshore, then the situation changes. Then the maximum loads occur. They do occur with a big storm. Yeah, I know you have another one of these big waves, so again a strong peak here. Cool. I'm gonna. Oh yeah, and I can show you a last thing. So can you see here? So the blade started vertical, and it's like it's been moving a little bit, and that's on purpose. When you have a storm or when you're stopping the wind turbine for whatever reason, well, if it's for maintenance, if it's for going up there and working, then you will put a brake so that nothing moves. But if not, then typically you want your blades to move a little bit, and that is because if the blades were always in the same position, the rotor was always in the same position, you would get a lot of wear and tear on the bearings. You know, because it will be like the bearings of the main shaft will always would always be facing the same way. So you want some rotation so that you kind of, you know, wear different parts of the whole system, I guess. And yeah, that's called idling. That's my wind turbine is idling.